Let's get the show on the road. Sweet. All right, welcome to the weekly Tendermint dev session, where we go into depth on one of our topics in Tendermint core. And today we have a guest with Luka, who I think collaborated with Žarko, who maybe can introduce us to what the background is, what the research scope was, and then Luka gets the floor and going to present to us Mempool alternative algorithms, as far as I understand.
Yes.
So basically I guess we are all kind of familiar. The Mempool design is quite simplistic for a time being, and that it's a potential performance bottleneck. And so we were looking with Luka at alternative designs, and the starting point was actually a sort of overall gossip guidelines which were provided to us by Max, who is a friend of mine and gossip expert. So we are not really like gossip expert, I would say. So at least Luka is now at least going in that direction. And so the choice of the alternatives was more or less provided by Max. And so you will see that they overall are quite reasonable, I think. And so we more or less, we haven't explored the huge space of gossip papers, but this research followed by Luka was more or less directed by this Max input. And yeah, Luka will present this and the overall conclusion. So yeah, we are kind of open. If some of you is aware of something we missed or something which would be also a viable alternative, and yeah, I guess the Luka floors is yours. You can share the screen instead.
Okay, thank you. Just give me a second. Everybody's supposed to see the screen, right?
Yep.
Mm-hmm.
Yeah, okay, great. So I shall begin. Hello, everyone. Today I will be talking about alternative mempool algorithms. First of all, I would like to thank you for inviting me to this presentation and for giving me the opportunity to present or to display the work that was the product of my senior thesis. I would like to introduce myself. My name is Luka Miletic, and I'm a master's student at the School of Electrical Engineering in Belgrade. I'm also a teaching assistant at the School of Electrical Engineering, and I am primarily interested in working on research and development projects regarding both distributed and automated systems. Before all else, I would like to give you a short overview of what it is that I will be discussing in further slides. So as Žarko said, our focus was analyzing the Tendermint's mempool. As all of you know, the Tendermint's mempool algorithm currently produces a very large overhead, and the goal of my thesis was to analyze the current solution and analyze alternative mempool algorithms or mempool designs in a way to discuss in a detailed manner 3 different approaches when it comes to gossiping data. Those 3 approaches can be found in literature. So first of them is a client-based approach, which is basically focused on client having the main role when gossiping data about its transactions. The second approach is called a structured overlay, and it is based on forming a structured overlay across the network of nodes, which basically means that we classify servers in the network into some structured groups. The third approach is a dynamic overlay, where the dynamic overlay is based on dynamically building a random network graph. Furthermore, as an addition to the formal analysis provided in the paper, I will explain the details of the simulation analysis, whose goal was to give comparison to the current algorithm used in Tendermint and the push-pull-push gossiping algorithm that can be found in literature. Simulation analysis will show that the push-pull-push gossiping algorithm shows significant improvement in comparison to the current solution used in the Mempool currently. My thesis can be found online, and if you follow the link here in the presentation, you can find the thesis available on GitHub. Okay, from the client's point of view, from client's perspective, there are two important events that need to occur. Client wants to have its transaction both executed and stored inside the blockchain. So if we denote those two events as conditions C1 and C2, we may state that in order to satisfy our client's needs, we have to actually guarantee that these two events will occur. As far as the consensus algorithm is concerned, as we know, validator set is chosen dynamically at each blockchain height, and it is unknown in advance. Furthermore, proposer is chosen uniformly at random from the validator set for every round that is instantiated during the consensus algorithm. So in order to guarantee that conditions C1 and C2 will be satisfied, we may conclude that a client's transaction must reach all the servers in the network, which basically means that our gossiping algorithm has to operate in such a manner that will guarantee that when a full node receives a client's transaction, that transaction will eventually somehow reach all the correct servers in the network. Okay, so first of all, the current solution. Just let me see if I can move the way. Okay, now it's great. First of all, the current solution. The current solution is very simple, and it is based on a node simply broadcasting information whenever it receives a new transaction. So when a client sends a transaction to a full node, what that node will do is simply broadcast information to everyone in its peer subset. However, it is obvious that this produces high levels of redundancy since nodes simply, every time they receive a transaction, just broadcast it into the network, which leads to servers in the network receiving a great deal of redundant messages. Furthermore, information about the received transaction is re-gossiped even to the sender. And a simple improvement would be actually not to do that, not to re-gossip the information to the sender, which would be a slight improvement to the current solution. Like I said, this algorithm produces a large overhead, and simulations have shown that this overhead amounts on somewhat 81.45% on average. That is simply a large overhead, so to speak. So in further presentation, I will present three algorithms based on three different approaches, which I have already mentioned. The first one is a client-based gossiping protocol. Client-based gossiping protocol is basically has an idea where a client has the main role when disseminating or when gossiping data about the transactions it wants to have executed and stored in a blockchain. So a client locally keeps track of two sets, the current validator set and the set of uncommitted transactions. Whenever a client wishes to have its transaction processed by the network, it merely has to send that transaction to everyone in the current validator set. The current validator set could be implemented, for example, by keeping track of IP addresses of every node in the validator set. Therefore, this implies that this algorithm has a requirement, and that is that all full nodes in the network should have public IP addresses, so that would enable a client to know who are the nodes that are in the validator set. Additionally, since the validator set is changed dynamically and it is changed for each blockchain height, a client somehow has to be notified about that. For that to be able, client will have a local oracle or a module that is able to keep track of all the changes in the validator set. And whenever a change in the validator set occurs, a client will receive an update message which contains information about IP addresses of everyone in the new validator set. Upon receiving the update message, client will resend only uncommitted transactions to everyone who are in the new validator set but are not in the old validator set. This will actually guarantee the satisfying of conditions C1 and C2, since we guarantee that each uncommitted transaction will be sent to everyone in the validator set. How do we update the set of uncommitted transactions? Well, simply when a transaction is executed and stored in a blockchain, a client will receive the commit message. Upon receiving that commit message, a client will actually update its local state and remove that transaction from the set of uncommitted transactions. Okay, so this client-based gossiping protocol, client-based solution, is interesting for enterprise setting and cannot be applied in a blockchain where there are no public IP addresses. The solution, actually, the performance of this solution is directly connected to the execution of the consensus algorithm, since as faster the consensus algorithm is executed, the less is the probability of us having to resend our uncommitted transaction to those who are in the new validator set. So this would be the first approach, the client-based gossiping protocol. And the next approach is based on having a structured overlay, or actually on classifying servers or nodes in the network into structured groups. The approach will be called tree clustering, and those groups are denoted as clusters. So now let's assume that we have a network of nodes where the entire network is divided into clusters. Each cluster contains multiple nodes within it. Clusters are formed according to some proximity criterion. For example, geographical criterion, nodes that are geographically close to one another form a cluster. Or, for example, round trip time or the number of hops between those nodes are some criteria that may enable us to somehow form a cluster. By forming a cluster, or actually by grouping nodes in the network into clusters, we achieve lower latency, since nodes are in some manner more proximate to one another than they were previously. We will also, in order to explain the tree clustering approach, introduce two types of links: intercluster links and intra-cluster links. Intercluster links are links between nodes in different clusters, whereas intra-cluster links are links between nodes in the same cluster. Okay, so far we've seen that by clustering nodes in the network, we reduce the latency. However, we still have redundancy, or we still have an overhead when it comes to receiving redundant messages. And the main, how should I put it, culprit behind behind servers receiving redundant messages is actually the fact that the graph of the network is a cyclic one. So if we could somehow remove that property of our network graph, we could probably reduce the overhead that exists. So following, we propose organizing servers in the network into a acyclic structure, which is actually a tree. First of all, I would like to explain how to solve the overhead problem within a cluster, and then I will explain how to solve the overhead problem within the entire network. So this illustration depicts how to solve the redundancy problem within a cluster only. So first of all, we will presume that nodes within a cluster now form a tree. And I will explain later how a transaction is gossiped when we have a tree within a cluster. First of all, let us assume, or actually for now, let us assume that we have nodes in the cluster that form a tree. Question arises as to who is responsible for managing the tree and who is responsible for handling membership requests, for example, when there is a new node that wishes to become a part of the cluster. We will suppose that the responsibility for that is on a set of state machine replication servers, and that set of servers actually manages the trees and handles membership requests. So basically, that set of servers has a consensus algorithm, and whenever there is a new member that should be added to the cluster, which implicitly means that there is a new node that should be added to the tree, the set of state machine replication servers should reach a consensus and decide where in that tree should the new node be added. Furthermore, this set of servers should somehow manage the tree and keep it as efficient as possible, for example, balanced or even complete. What's more, it is good practice to periodically shuffle the tree because, for example, if you have leaf nodes in a tree, leaf nodes gossip information a lot less than, for example, interior nodes in a tree. Therefore, in case they have a high bandwidth, they are underutilized. So in order to optimally utilize the bandwidth of all nodes in a cluster, we should periodically shuffle the tree, or actually state machine replication servers should periodically shuffle the tree. So, okay, I've explained how do we form a tree inside a cluster, and now I will explain how the information is disseminated, how the information is gossiped when we have a tree in a cluster. we will adopt two principles, two different manners of gossiping. Upward gossiping, which basically means that a node in a tree sends information to its parent, and downward gossiping, which basically means that a node sends information about a transaction to its children. So there are certain rules for upward gossiping and for downward gossiping. Downward gossiping is always performed, whereas upward gossiping is performed only when a full node, for example this one, receives a transaction from a client or from a child. In that case, that full node has to gossip information about which it just received to its parent in the tree. So, okay, this was explaining how to solve the overhead problem within a cluster. We still haven't solved the overhead problem within the entire network. So in order to do so, the only thing we have to do is actually generalize the idea behind tree clustering inside a cluster. So if we now made our clusters, so our entire network that is divided into clusters, and if we made those clusters now form a tree, we would actually get a solution which provides no overhead at all when it comes to receiving redundant messages. Because we only have unidirectional links in this data structure, and whenever any node in the network receives information, it should only disseminate it according to the aforementioned rules of upward gossiping and downward gossiping. Additionally, it should be observed that upward gossiping is now also necessary even in the case of a client, of a full node, receiving information about its intercluster child, which actually means, for example, if this node received information from a node which was in another cluster, which is its child, it should also perform upward gossiping to its parent cluster. So this solution is actually good because there is no redundant messages that are received by servers in the network. However, state machine replication servers do produce an overhead, do impose a certain level of overhead because simply they have to manage the tree, they have to reach a consensus, and that is a non-negligible cost. Okay, so these were the first two approaches, and the first two approaches were, so to speak, ideal because they provided no redundancy when it comes to receiving redundant messages. They provided no overhead in that sense. However, some of the concepts of the first two solutions are still open to discussion, and some of those concepts are still subject to much ongoing research. So if we would like to implement the first two solutions, we would have to do a bit more research to accomplish that. On the other hand, the third solution I'm going to propose is relatively easy to implement, and that is its key advantage. It is 100% gossip-based, and it is actually it can actually very realistically be implemented in an existing system. So it is based actually on three different protocols described in literature in three different papers. The first protocol is called push-pull-push gossiping protocol. The second protocol is called heterogeneity-aware protocol, and the third protocol is called peer sampling service. So these are all three separate algorithms described in literature. However, their combination applied to the Tendermint network and to the Mempool gossiping in Tendermint should, or actually would, provide significant improvement. So like I said, this is 100% gossip-based and dynamic algorithm, and it is based on randomly creating a network graph. First of all, in order to explain the first two protocols of this algorithm, we will adopt a presumption that is not correct when it comes to the Tendermint network. And that presumption is that each node in the network has to know about every other node in the network. This is simply because this will enable an easier explanation of push-pull-push gossiping protocol and heterogeneity-aware protocol. However, as we know, Tendermint is not. Tendermint is a wide area network where nodes are not a part of a single administrative domain, and therefore there is no way that a node can actually know IP addresses of every other node in the network. So for explaining the first two parts of this final algorithm, we will adopt the assumption that a server in the network, a full node in the network, knows about every other node. In order to explain how to apply this solution in the Tendermint network, I will introduce the peer sampling service, which will then explain how to neglect the fact that the node should know about every other node in the network and how to apply this algorithm in a wide area setting. So from now on, we will assume that a node knows about every other node in the network, and then when it gossips information, it simply periodically selects a certain number of nodes from that network, and thus implicitly creates a peer subset and disseminates data to those in the peer subset. Let the size of that peer subset be denoted with F, and let that peer subset be of the same size for each node in the network. So periodically, each node in the network selects the same number of nodes from the set of all other nodes and disseminates information about transactions to that peer subset. Okay, so first of all, I would like to explain the push-pull-push gossiping algorithm. The push-pull-push gossiping algorithm was also a part of a simulation analysis. So it is actually a key algorithm and that provided significant improvement in comparison to the current solution. So a push-pull-push gossiping algorithm is an algorithm which is actually a three-way handshake protocol, which consists of three different messages: propose message, request message, and serve message. Additional message exchanged between a client node and a server node is a so-called published message. The key idea behind the push-pull-push gossiping algorithm is to disseminate information about clients' identifiers, and not to disseminate information about, not about clients' identifiers, about transactions identifiers. So the key idea is to disseminate information about transactions identifiers and not to disseminate the entire transaction. By doing so, we achieve that a transaction will be disseminated or gossip only when it has explicitly been requested. So how does this work? When a full node receives a published message from a client, and let's say that the published message contains a client's transaction, that full node will add that transaction to its mempool and will somehow remember its identifier. And a full node will do that for every transaction it received from a client. When a certain period of time passes, which means that a full node does this periodically, that full node will gossip information about every transaction identifier it had learned from the previous gossip until the current gossip. This model is a so-called infect and die model, where a full node disseminates information about every transaction identifier it found out about from the previous gossip until the current gossip, and then somehow forgets about this information. So a full node will disseminate information about identifiers only once in a proposed message. It is important that this proposed message contains only transactions identifiers. When another full node receives a proposed message, it will check which of those identifiers, which of the transactions corresponding to the identifiers received in the proposed message it does not have inside its mempool. It will then send a request message to the original full node who sent the proposed message, and the request message will contain only identifiers of those transactions that are not in the mempool of this full node. When the original full node receives the request message, it will reply with a serve message, and the serve message will actually contain an entire transaction, an actual transaction. So we may conclude and we may see that the transaction is sent only and only then when it has been explicitly requested. There is no disseminating, there is no gossiping data about the transaction when it is actually not needed. So this is actually the key feature of the push-pull-push gossiping algorithm. So okay, this was the push-pull-push. And the next one, the second protocol of the final algorithm, is called HEAP. Like I said, we suppose that a node knows about every other node in the network. So periodically, it simply selects a fixed number of IP addresses from that set, and it implicitly creates a peer subset and disseminates information to everyone in the peer subset. However, not all nodes in the network have the same bandwidth. But therefore, by assuming that all nodes in the network should have the same fan-out or the same size of the peer subset, we may somehow overload a certain node, whereas we may underload some other node because it has a higher bandwidth and we are not utilizing it enough. HEAP protocol is based on periodically exchanging aggregation messages, where aggregation messages contain information about capabilities of other nodes. Capability could be, for example, a bandwidth of a node. So let us assume that it is a bandwidth and that servers in the network periodically exchange information about each other's bandwidth. This leads to all the servers in the network throughout time learning about capabilities of other nodes in the network. And when disseminating data, a full node can adjust its fan-out or calculate the preferred size of its peer subset simply by using an equation provided in HEAP. Therefore, the core idea behind the HEAP protocol is to actually adjust the node's fan out in order to optimally use its bandwidth. And the third part of this algorithm is called the peer sampling service. The peer sampling service, by explaining the peer sampling service, I will explain how this algorithm is, applicable in a wide area network. So peer sampling service is also a gossiping algorithm. It is also a gossiping protocol, which is responsible for exchanging information between nodes about their peer subsets. So peer sampling service enables full nodes in the network to learn about their peer subsets. And how does it do that? Well, let us suppose that each full node now has a partial view. Partial view is a list of node descriptors where one descriptor contains IP address of a peer and the number of hops to that peer. So basically, this partial view is actually a peer subset. This is just another notation that can be found in literature for a peer subset. And we have a partial view that is a list of node descriptors, and periodically, in the peer sampling service protocol, which uses active thread for initiating communication and passive thread for receiving information, nodes in the network will exchange information about their partial views. This will lead to nodes learning about one another, learning about IP addresses, and learning about other nodes in the network, and thus forming their peer subset in a wide area setting. So what is actually the final solution? How do we combine all of the three aforementioned protocols into one? We use the push-pull-push gossiping protocol to disseminate or to gossip information about a transactions identifier only, and to send the actual transactions only when it has been explicitly requested. So we delay sending the actual transaction until it has been explicitly requested by some other node in the network. We use the HEAP protocol, or the heterogeneity aware protocol, to adjust the nodes fan out, or actually to adjust the number of nodes from the peer subset that will receive our message when we are disseminating a message. And that is done because we want to optimally use the bandwidth of our node. And we use the peer sampling service to enable servers to actually form that dynamic overlay I was talking about, to actually form in a dynamic manner a random network graph. So this would be everything as far as the formal analysis of those three different approaches I mentioned at the beginning is concerned. To finish my presentation, I would like to present the details of the simulation analysis. Simulation analysis was focused on comparing the push-pull-push gossiping algorithm, so this one, to the current solution used in Tendermint. Simulator was written in Java, and it is a simulator simulates a client-server architecture where a client sends a fixed number of transactions to a set of randomly selected servers and waits until all the servers have received all the transactions. So it should be observed that it isn't important that we only have one client, because the accent here, the focus on this simulation was gossiping data and not the number of clients. So we have a client-server architecture where a client sends a fixed number of transactions into the network and waits until all of those transactions have been received by all of the servers. This is how a single simulation is performed. So since this is a simulation, I was supposed to adopt certain metrics, and there were three different types of metrics. First metric is overhead. Overhead is expressed in the percentage of redundant transactions received by a full node. Delay is expressed in milliseconds, and number of hops, which is represented actually by the average maximum number of hops, actually is a metric that depicts the average maximum depth of a network graph. So as we know, the number of hops actually represents the number of servers when we actually disseminate a message from the source server to the destination server. The number of servers on a message path from the source server to the destination server represents that number of hops. So the simulation was focused on comparing these three metrics with the current solution and with the push-pull-push algorithm. There was one presumption in the simulation analysis, and that is that the network graph is always connected. So the minimum size of a peer subset was 1, whereas simulations were executed for three different average peer subset sizes. They were LNN, 2LNN, and 3LNN. And this was primarily done so that we could illustrate how the metrics change when we increase the size of the peer subset. Okay, so before I present the results of the simulation, I would like to point out an important fact. And that is, I would like to explain how I was calculating the overhead percentage. As you may have noticed, or may have not because I did not explain it, the only redundancy that exists when using the push-pull-push gossiping protocol is when we send a proposed message. Because when a full node receives a proposed message, that proposed message can contain identifiers of transactions that are already inside my mempool. Because whenever a node adds a transaction to its mempool, it also remembers its identifier and gossips that identifier in the future gossiping when the gossiping period elapses next time. Therefore, when a full node receives a proposed message, that proposed message can contain information about redundant transaction identifiers which are already inside that full node's mempool. Because of that, redundancy is present with the push-pull-push gossiping algorithm, but only when it comes to identifiers. With the current solution, redundancy is present when it comes to entire transactions. Therefore, in order to properly express the overhead percentage, that percentage was expressed in the number of redundant transactions. So, for example, if I've received 100 transactions and the overhead percentage is 75%, it means that out of 100 messages, 75 of them were redundant and 25 were actually useful. So how did I then calculate the overhead for the push-pull-push gossiping algorithm, since the redundancy only exists when receiving identifiers? I just scaled those results by comparing the transaction size and the identifier size. Identifier in Bitcoin network is calculated using a SHA-256 hash function, and the size of that identifier is 32 bytes, whereas the average transaction size in Bitcoin is around 550 bytes, which means that the transaction is approximately 17 times larger than its identifier. So when calculating the overhead of the push-pull-push gossiping algorithm, I calculated in a way that I suppose that whenever I receive roughly 17 identifiers, I have actually received one redundant transaction. And that is a way in which I have actually calculated the overhead. So finally, I would like to present to you simulation results. These simulation results first are represented by graphs. There are three charts, actually, so to speak. The top left chart represents results of the simulation when the average size of the peer subset is ln. The chart in the top right-hand corner represents the results when the average size of the peer subset was 2 ln, and this one in the lower left-hand corner represents results when the average size of the peer subset was 3 ln. These three charts represent the average redundancy expressed in the percentage of redundant of transactions received, and that is shown on the y-axis. On the x-axis, we have the number of servers. So basically, simulations were executed for different number of servers, but always with a fixed number of 200 transactions. When looking at these charts, I would like to point out that the smaller value is a better value, since if we have a smaller overhead, we achieve better results. A dashed line represents push-pull-push. The dashed line, represents current solution, whereas the bold line represents the push-pull-push gossiping algorithm. So we may see that the push-pull-push gossiping algorithm shows significant improvements regarding redundancy, especially for the optimal size of the peer subset, which is ln. When increasing the size of the peer subset, we may see that the redundancy increases as well, but this is expected since by increasing the peer subset, we have more links to the network graph, and a transaction can travel through more paths and reach the same server via many different paths, and thus leading to the reception of a larger number of redundant messages. Nevertheless, the solution, the push-pull-push gossiping algorithm, shows significant improvement comparing to the current solution, since on average it reduces the redundancy by roughly 56%. I calculated that beforehand. So this is as far as the redundancy is concerned. As far as the other metric, delay, as far as the delay is concerned, there are also three charts for ln, for 2 ln, and for 3 ln. The y-axis represents the average delay expressed in milliseconds, and we may see that The push-pull-push has a slightly larger delay than the current solution, and this is also expected since the push-pull-push algorithm is a three-way handshake protocol, where the current solution is an algorithm which simply broadcasts information about transaction. And one more thing, I would like to explain how I generated these delays. Simply, when generating the network graph, I assumed that links between nodes in the network graph can be of two types, LAN link and WAN link. And in accordance with the type of the link, I generated different values for delay when gossiping the message. So it was from 1 to 3 milliseconds for LAN links, or from 10 to 70 milliseconds for WAN links. And this delay generation was merely illustrative, and it was used to show what is the ratio between the delay of the current solution and between the delay in the push-pull-push algorithm. When increasing the size of the peer subset, we may see that the delay decreases, and this is also expected since by having more nodes in the more links in the network graph, we achieve that our transaction can travel more quickly through the network. And the final metric was average maximum hop count. Like I said, average maximum hop count depicts the average depth of the network graph, or else shows how many servers on average did the transaction have to go through at most. So as we can see from these charts, where on the y-axis, the average maximum hop count is expressed in the number of servers. The push-pull-push algorithm also has smaller values for the average maximum hop count. Now, I would like to explain why is that so. When we have a client, and when that client sends information to its nearest pool node, that pool node will simply send propose message to everyone in its peer subset. That proposed message will reach everyone in the peer subset. Those members of the peer subset will send a request message to the original sender, and then that sender will respond to everyone in the peer subset by sending them a serve message. This makes the hop count minimal, and this is simply recursively reflected onto the entire network. In the current solution, if we have, for example, 5 LAN links and 1 WAN link, transaction can travel more quickly through those 5 LAN links than through 1 WAN link, and thus producing a larger average maximum hop count. Okay, so that is it as far as the metrics are concerned. And to conclude, or to give you some concluding remarks regarding my presentation, I would like to point out that when using the push-pull-push gossiping algorithm, we present a promising alternative to the current solution, because as we saw, overhead is significantly improved. It is significantly smaller when using the push-pull-push gossiping algorithm because we only disseminate a client's transactions identifier. Furthermore, if we somehow manage to reduce the size of a transactions identifier, for example, if it is a local sequence number followed by a client's public IP address or something, if we manage to somehow reduce the size of an identifier, the improvement would be even more significant. So the overhead is significantly smaller than it is with the current solution. However, the delay is slightly larger, but the number of hops is still smaller. When increasing the fan-out, or the average size of the peer subset, we actually increase the redundancy, but decrease the delay and the number of hops. This is actually an acceptable compromise, at least I think so, because we can actually maybe find such a value for the maximum fan-out size so that the redundancy never exceeds a certain threshold. Maybe even that's a possibility. And as far as future work is concerned, it would be interesting to see how it is possible to implement the first 2 algorithms, because as I've stated before, some of their concepts are open to discussion and are subject of ongoing research and are currently being dealt with by many scientists around the world. It will also be very, very interesting to do real experiments in LAN and WAN networks and local area network and wide area network settings to see, to actually observe the behavior of the push-pull-push gossiping algorithm in comparison to the current solution, and to actually, in a much more clearer manner, compare their capabilities and their abilities according to the aforementioned metrics. It would also be a good idea to use an idea from bar gossip. Bar gossip is an algorithm which is similar to the push-pull-push gossiping algorithm, and I think Žarko will tell you a little bit more about that. So that would be it. Thank you for your attention, and that would be all. That's it. Thanks. Thank you again.
Thank you so much for this very insightful, deep rundown. I think was really high quality. Maybe we have straight up questions. Otherwise, Zarko, maybe you can comment on the bar algorithm. Dev, you wanna ask questions?
Yeah. Thanks for the presentation. It's really good.
Thank you.
I was wondering, can we use to your final note? I think we can definitely lower the transaction identifier to be like 15 bytes very securely, which would be good. But I was wondering, from your original premises, like you had the constraint that's you want every full node in the network to receive a transaction. I think that was C2.
Yes.
Could we reduce that to be something more probabilistic, like perhaps 90%? Does it make sense to reduce that to be 90% of the nodes receive a transaction? Because we only need one proposer to propose it.
Yes, I understand. Well, what I proposed is simply something that guarantees that the client's conditions will be satisfied. However, if we guarantee it with some probability, then probably we will be able to have only a probabilistic solution, if I understood the question.
Do you know of any ways that might like even further lower the amount of bandwidth used?
The amount of bandwidth.
Overhead. My bad.
Overhead. The amount of some other matters that could even more reduce the overhead.
Yes, I was asking like if we made it probabilistic, does that seem doable or not really?
Well, I don't know actually. I mean, there's many things.
It's actually, we were thinking about this. It's just, I mean, it's really, it seems like a good idea, and we discussed also this idea because, as you said, like we don't need to reach all validators. It's just that the guarantees, as Luka said, would be probabilistic, and so I think that more or less having such probabilistic solution from one of those proposed is definitely possible. It's just that we'll probably constrain somehow pushing data at some point, and it's just it's a bit more tricky to decide when we'll stop, when is enough, or it could lead potentially to a bit more complex algorithm. But from the resource point of view, this definitely seems like interesting approach to give it a try, definitely.
Like for example, in the tree gossiping algorithm, it seemed that you could have you could eliminate a lot of inter tree communication, and by having a client send into a couple of trees and only have trees communicate with other trees with like a probabilistic model.
Yeah, definitely. The problem with tree-based approaches are that they seems quite tricky to implement because we need to somehow manage the trees, and as we said here, like we'll need to find a way to manage this state machines, replicas or for each tree, and then also overall. So this adds
exactly
overhead resource wise, and from the implementation point of view also seems like quite heavy. So it seems it has some benefit, but we haven't decided to follow up with this approach because it felt really complex, and the implementation overhead was like too high.
Okay.
That's what I was going to tell. In this tree clustering model, there are too many missing details. Like, what if the root of a tree goes down? Is the tree supposed to rebalance itself? Or like it's very hard to maintain this exact tree structure within the cluster.
Yes, well, yeah.
Like, so far, I'm not aware of any like production system doing that. There are many systems which does clustering, but they use some consensus algorithm to agree on a common structure like a list or something very simple, not a tree.
In the push-pull-push, is a single ID proposed or is it batched? And vice versa
no.
in the request?
Yeah, so well, when sending a proposed message, I hope you can see this.
Yeah.
Yeah. When sending a proposed message, a pull node will propose a list of identifiers. So, for example, since it proposes messages on every gossiping period, from the first gossiping period until the next gossiping period, it simply collects information about received transactions identifiers and stores them inside a list. So when the gossiping period elapses, it only sends the entire list of those identifiers.
Cool. And for the aggregation part, what other capabilities could you imagine besides bandwidth?
Yeah, well, in the paper about the HEAP protocol, it is said that it is implementation dependent. However, it is, I think, very much possible that the capabilities should be bandwidth of other nodes, and therefore we could adjust the fan out of a node by the equation that is presented in HEAP. Simply by having nodes exchange information about their capabilities. That way we would learn, for example, about average bandwidth in the network and apply the equation and get the optimal fan out for a node.
And to the last point, you mentioned that you would like to run actual experiments. Would your simulation framework, would that be usable to be fired against real clusters?
You mean would my simulator currently used would I be able to modify it so that it could be, well, I think yes, it is currently a concurrent application, but I think it could easily be modified to become a distributed application and to actually be used in an experimental setting. And I think that would be really useful, actually. It would really depict the properties of the push-pull-push algorithm in a much, much clearer way.
And actually, I was hoping for implementing this in the context of Tendermint and then having our experiments there. So it will be a bit more work, but I think this will be more interesting.
And is there any prior art, like any implementation of the protocols you described? Is it somewhere used, or is it purely research at this point?
I'm sorry, you mean about the push-pull-push?
Yeah, like the algorithms you described last. Like, is there any implementation in the wild that can be looked at, or that has proven this works in setups like ours?
Okay, I understand what you're saying. I mean, I'm not really aware of that, but it is probably in some of those papers it is written. I think when I was reading them, it was stated that there are systems that rely and that use these protocols and these algorithms, and each of those papers actually provided a thorough experimental analysis followed by mathematical proofs that these algorithms actually provide good performance.
Cool. Could you share those references just for us to catch up on?
Yes, of course.
And if there are no other questions, we approaching the end. Maybe Zako, a little primer on the bar gossip, just to get everyone excited, maybe for a future session.
Yeah. So bar is, in essence, it's very similar to this push-pull-push because it's also it's kind of also three-way protocol there. The difference is that it has a cryptographic security. These algorithms in general are not really designed for Byzantine fault-tolerant model, and so like Anton said, for example, tree-based one are not really. It's known that they don't behave well in a faulty environment. So if you have a high churn of nodes, going down, they will not probably behave very well. So bar is contrary design from the beginning for decentralized open network, and therefore it has a built-in cryptographic security. So whenever you engage in a gossip round, in this proposed phase, there is some promise which is being made, and so then later when you serve, if you don't fulfill promise, this is a proof of misbehavior. And it can be used against you, so you are kicked out, basically from the network. So this is it's really very simple, I would say, relatively straightforward idea, but I think it's a very powerful one. And even in our context where we are having a permanent connection between nodes, also for consensus messages, for gossiping consensus messages, I think it can be adapted. And in the bar paper, so there is a series of bar paper. The one is about bar gossip, and then there is, I think, at least 3 more, which are more like about consensus, and then some example applications. So bar means Byzantine, altruistic, and rational. So they are, from the design point of view, assuming that some nodes in the network will be faulty, so Byzantine. Some will be altruistic, which means they will not behave according to the protocol if it's in their favor. And altruistic are like what we assume as a correct nodes. They will always follow the protocol. And the goal is to design protocol in such a way that even if all nodes are altruistic, are rational, it will still guarantee sufficiently good throughput and latency. I just wanted to mention one more thing, that they analyzed in the paper also coalition, which I think also in our case are quite interesting. Because if in gossip networks some participants establish direct links and decide to ignore gossip, how it might affect overall behavior. And so they were analyzing also behavior of algorithm in those circumstances. And then also when they inject some percentage of Byzantine nodes and when all are rational, etc. And they're able to prove that even if all nodes are rational, the suggested behavior of the protocol is there, it's the best win for them. It's basically Nash equilibrium because there is a game theoretical analysis around. So I think in general that bar is super interesting for us. And it would be really cool if we are more familiar with this research, and if we start slowly to use those ideas when in our to check first how bad or good we are with respect to particular attacks, and also to start using those ideas to move forward our protocol.
Perfect. Thanks so much for the rundown, Luka. Thanks heaps for this presentation. Very insightful. I think this is a great resource going forward, like not only for us, but for everyone in the company and maybe in the community. And definitely well of inspiration for what we can improve in the mempool. And hopefully we can follow up on this. Maybe you would be willing to share your slides so we can put it in the video description and provide that as well.
Yes, of course. I will share my slides, both the slides and references.
Perfect. And hopefully we're gonna see you in the not so distant future. For everyone else, thanks for joining today, and see you next week for the next one. We haven't decided on the topic yet. We'll do that during the week, and then we're gonna be here same time next week on Monday. Thank you so much.
Can we make a GitHub issue and continue discussion on this?
Absolutely.
This sounds like a forum post, not a GitHub issue, maybe? No. All right, bad idea. Talk to everyone soon.
Okay, thank you for the presentation.
Thank you so much. All right.
Thank you.
Talk in a bit.
Ben.
Bye-bye.
Bye.
Bye, everyone.
Thanks.